Hi everyone, welcome back to video lecture series on RA6M5 RA microcontroller. In this video, I'll show you how to implement a secure bootloader on the RA6M RA6M5 using MCUboot in protected mode with internal code flash. We'll set up the bootloader, build a sign application, and define the flash layout required for secure updates. A bootloader is the first firmware to run at power-up, and on RA6M devices it forms the root of trust. MCUboot verifies the application using cryptographic signatures and only boots it if the image is authentic. In protected mode, the RA6M5 uses securely stored keys to prevent tampering and block unauthorized firmware, while MCUboot structures flash into partitions that support safe updates and rollback protection. This process gives the RA6M5 a secure update path, ensuring that only verified firmware can run. In the next steps, we'll generate the signed image and prepare it for loading through the bootloader. We begin by creating a bare metal project, which will act as our bootloader. Open eSquared Studio, then create a new project by clicking on the File icon, then select New, then select RA6M C++ project, then select RA6M RA project. A new dialog box will appear. You can give a name to your project here. After naming your project, click on the Next button. From this drop-down menu, select the RA6M5 board. Choose the GNU ARM embedded toolchain. After board selection, click on Next. After that, select Flat, Non-Trust Zone Project. For Smart Bundles, select the None option, then click on Next. Now select Executable and No RTOS option. Now select Bare Metal Minimal, then click on the Finish button. Now the IDE will take some time to configure your project. Now click on the Open Perspective button to open the FSP configuration file. Once the workspace opens, add the MCUboot stack and delete the I/O port stack. Since the SCE9 accelerated, MCUboot requires high memory. Add the bootloader stack by selecting New Stack, Bootloader, MCUboot. Next, add the cryptography stack, which MCUboot uses internally for ECDSA signature verification. Add the flash module, rFlash, because MCUboot must access internal code flash to read and validate the application image. Also add the example keys, including the public key that will later be used to sign application images. In the Flash Stack properties, enable Code Flash programming and disable Data Flash background operation. In the Embedded's TL Script Stack properties, under General, undefine the threading options, threading LT and threading C, and define memory code for allocation. Under the BSP tab, increase both the heap and stack sizes to 0x2000, as MCUboot's cryptographic operations require additional memory. Generate the project content. Next, open HAL-entry.c. Before making changes, we need to comment out the I/O port API. To do this, go to HAL-warmstart.c and comment out the I/O port initialization code. After that, return to HAL-entry.c. Go to Developer Assistance tab, navigate to HAL/common/MCUboot and add the Quick Setup API. Then call this API inside the main function. Once the call is added, build the project. Select the project and run a full build. The build may take a little time to complete. Now we create the application image that MCUboot will authenticate and run. Create a new bare metal C/C++ project for your application, selecting EKRA6M5 and the GNU toolchain. Link this project to the bootloader project by choosing the bare metal linker project. Select the bare metal Blinky project and finish in In the application project properties, add environment variables for MCUboot image signing, key and then MCUboot app bin converter. Set the MCUboot image version to 1.0.0, apply and close. Then build the application project. We will get an error related to the Flash layout. This is expected. To resolve this, create a solution project. Select C++ project, FSP Solution Advanced. Name the solution project, then add both the bootloader and the application projects. Open solution.xml and navigate to the Memory tab. Define the partitions for the bootloader, the primary application image, the image header, the secondary image, and the scratch area if you're using upgrade mode. These partitions map out the complete Flash layout and tell MCUboot exactly where each signed image and metadata will be stored. This layout is also used by the signing tools to generate valid firmware binaries. Once the partitions are set, save the solution XML and rebuild the solution project. Once the signed application image is built, the output folder will contain the final signed binary that MCUboot can authenticate. Now we need to flash and debug the application together with MCUboot. Open Debug Configurations and select Debug Flash. In the Startup settings, set the PC start address to match the beginning of your application partition, and select the bootloader ELF. Then add the signed application binary, apply the settings, and start the debug session. This will switch you to the FSP debug perspective. From here, MCUboot will authenticate the signed image, transfer control to the application, and you should see the LED begin blinking once the jump to the application is successful.